Alright, we're ready for part 3, chemical bonding, Lewis dot structures, naming compounds, and writing formulas. And we're still working with those teaks where you have to name the compounds, write the chemical formulas, construct electron dot models of the formulas, and describe the nature of metallic bonding. Finally, make figure out what the molecular geometry would be for some certain ones. Alright, so we start off next with ionic bonding. And ionic bonding is when you transfer electrons. The metals are always going to give up the electrons, so they're going to become positive cations, and the non-metals are going to always take the electrons, and they're going to become negative anions. My name's Bond. Ionic bond. Taken, not shared. Isn't that great? I love that. I love that. You should too. So ionic compounds are made of positive and negative ions, and they're combined so that the numbers of positive and negative charges are always going to equal 0 is what it should say. I don't know what happened after equal. But they're always going to equal 0. So when you have a negative charge and a positive charge, when you add them together and they're in the right ratios, they should be equal to 0. So you have a positive cation and negative anion, and they stick together because opposites attract. You guys already know that. Now, instead of calling them all molecules, what we typically do is call them a formula unit. So the smallest piece or the smallest section of an ionic compound is called a formula unit. It shows the types and the number of ions in an ionic compound. So again, positive ion is the cation, and it always goes first. The term formula unit is used instead of molecule. Ions are more stable because they combine in crystal formation. What that means is, when we have a covalent compound like H2O, that's it. It's all its own little bitty unit there. But let's say we have an ionic compound like NaCl, sodium chloride. Well, it's not just one Na and one Cl, although you can get that as the smallest unit. If you have a positive Na and a negative Cl, well, you also have a positive and negative Na and Cl all around them, and all the positives are attracted to all the negatives, whichever one they're closest to. So you have all these positive and negative attractions all three-dimensionally, and it keeps them all together pretty strongly. There are some certain characteristics of ionic compounds, just like we saw with covalent compounds. They have much higher melting and boiling points than the covalent compounds. They exist as crystals that are brittle. Shifting the structure or striking it will cause cleavage. You guys remember cleavage from your 8th grade science, and that means they break along certain patterns. Many of these are soluble in water. Not every single one, but a large majority of them are soluble in water. On your star chart, there is a table that says solubility on it in water. They also conduct electricity when they're dissolved in water or when they're melted. Why did the white bear dissolve in water? Because it was polar. Okay, you remember in the last section we said like dissolves like, right? So we have covalent when they're supposed to share electrons, but in polar covalent, one side tends to pull more tightly on the electrons than the other, so we have one side negative, one side positive. Well, in ionic compounds, they always have one end positive and one end negative. So it makes sense if they have poles, they're ionic, and they will be dissolved in polar covalent stuff. So like dissolves like. Water is one of the most important examples of polar covalent compounds. Most things dissolve in water, and that's why water tends to be called the universal solvent. So the next thing we have on here are polyatomic ions. Poly is many, so we've got this ion that's made of more than one atom. Basically what happens is you have several nonmetals. They've been bonded together, and they tend to stick together as a group, kind of like one chunk together. And we call these polyatomic ions. So they're covalently bonded, but they end up having a charge. And they have both ionic and molecular characteristics, and they combine with other ions to form ionic compounds. So this chunk, instead of just having a non-metal, one individual atom or one individual element, you have a chunk of non-metallic elements that kind of band together and stick together as little chunks, and they bond with a metal over on the other side for the most part. That's a polyatomic, kind of a weird one, but when we start naming the compounds and writing out the formulas, it'll make a little bit more sense to you. Look at your star chart. It's got a list over on the left-hand side of common polyatomic ions. So they have their own names. So if you have one where it's NO3, that means that nitrogen bonded with 3 oxygens tends to stay together as a chunk when it's in a compound. And they give it a special name. Instead of calling it nitrogen and oxygen, they call it nitrate. Sulfate, SO4, with a -2 charge. So these things are bonded together, but they have a charge. And whenever you have these charges, like charges repel, opposite charges attract. So they're attracted to those metal ions because they have a negative charge. The metals are always going to have a positive charge. They're attracted to that way. Oh, there goes part 3.